So this here is an F-35 warplane, and it's kind of interesting because it has the capability of turning its rear thruster downwards and for it to open a small extra engine hole at the front end of the aircraft. Now this enables it to direct its thrust directly towards the ground, counteracting the weight of the aircraft, enabling this aeroplane to stop and hover in mid-air. Now we might be interested in how we could represent those forces, and we represent it with a free body diagram. A free body diagram is a simplified version of the object but with the forces drawn on it. Free body diagram. So the first thing we draw with a free body diagram is the object. We normally represent it with a big dot in the centre, and use a ruler to draw the forces on. Now the size of these forces are important. We have to draw it to scale. So what I'm going to do is I'm going to draw a 20 centimetre line straight down to there. I'm going to label it capital W for the weight of the aircraft. Now, for it to hover, it's going to have to produce exactly the same amount of thrust in the opposite direction for it to hover. And we could call that T for thrust. Now, what you can see with this free body diagram is that it's really simple. That I've not drawn it as an extended object, I've drawn it as a dot. And this here basically demonstrates what's going on. Now, what I could do to make it more detailed is I could represent the actual aircraft like this. This is the aeroplane. I could represent that the weight was acting downwards and that two smaller forces were acting up from the two engines. I could do that, but it's not necessary right now. Notice that the thrust arrows are pointing up, even though those thrusters are pointing down. It's confusing, isn't it? But just think, if the hot air coming out of those thrusters is going down and the plane is getting pushed up, that's because it's trying to balance its own weight. Now, the reason why we can draw forces like this is because they're vectors. Vector quantities are things that we can measure that have a very particular direction. Weight is acting downwards. In this case, thrust is acting upwards. And so we can draw it on this diagram, and drawn to scale you can see that neither one of these, weight or thrust, is larger than the other. If this was a toy and it was producing 100 newtons of thrust, and that it was 100 newtons of weight, you can see that these two added together would just cancel out to zero. There would be no overall force acting on this. Now we say in physics there's no resultant force. Sometimes we say there's no unbalanced force because the forces here are balanced. What about a different example? What about the example here with the Soyuz rocket? Now the Soyuz rocket is going to be very similar to the aeroplane with one obvious difference. What's going to happen with the Soyuz rocket is it's still going to have its weight acting down, so we draw the middle of the free body diagram and say it weighs the same as the aeroplane, which I'm sure it doesn't. But now, and there is W for capital weight, capital W for weight, now it's going to have a much larger thrust than weight. Now this means that if this was minus 100 newtons and this was plus 600 newtons, then you can see that overall there's going to be upward force of 500 newtons. The part that isn't cancelled out when you subtract 100 from 600. It means that there is not going to be a balanced force situation here. This is unbalanced. And being unbalanced, it means that there is a resultant force upwards, causing the rocket to accelerate upwards towards space. Now these free body diagrams can get more complex. Here with this Typhoon, this is an aeroplane in the sort of conventional sense. It flies forwards through the air. So that means that there's going to be forces acting on this in two different dimensions, both the up and down dimension and the forward and backwards dimension. So what we need to do is we need to draw a free body diagram that represents all of those forces. So first of all, we can draw on the plane's weight and draw that one down here. That is the weight. And then there's going to be a force that is acting against the weight. And that, for a plane that is keeping a constant height, is going to be the lift. As the air flows across the wings of the aeroplane, then an upward force is generated on the plane. But the plane is flying forwards. So we're going to have to draw a force going forwards in the direction of motion of the aeroplane. And so this is probably the thrust of the aeroplane. Now, like that, this aeroplane would accelerate forwards, getting faster and faster. But what I'm going to say is that this aeroplane has something acting backwards against the direction it is thrusting, and that is the air resistance. Here, this plane is in fact balanced. The forward thrust is just overcoming the air resistance, the drag pulling it back. This plane is flying at constant speed. These free body diagrams allow us to understand what is happening with the forces and help us to determine whether or not the situation is one where the forces are balanced or whether or not there is an unbalanced resultant force. This is Roscoe's Spectrum Analysis, and this book is dated 1870. Nice old book, this. And I'm just going to put it here on my inclined plane, and notice that it doesn't move. In fact, what's happening here is there is no change in motion whatsoever. So this must represent a situation where there are no unbalanced forces. There's no resultant force. So what are the forces acting in this situation? Why does it not just slide down? In which direction is friction happening, for example? Well, we need to draw this as a free body diagram and consider what is happening both in the vertical direction and the horizontal. So now our free body diagram gets an additional thing on it. It gets the slope. And so here I will draw my inclined plane by drawing around my ruler. And I'm going to draw on it my book. Here it is. Now, where on this book do I draw my arrows? Well, we use the centre of gravity. The point in the centre of the object, from which point, or on which point, all of the forces are said to act. So what forces are present that enables the book to stay motionless on the surface? Well, the very first one we should draw, it's always the most obvious, is the weight acting downwards. Very few situations where we're not going to have that as the first force to draw. But now we must draw the reaction force. And here's a curious thing. If I was to draw this same setup with a horizontal ruler like this, what is going to go on if I, for example, placed my book flat down on a table? So rather than had it here, what if I put it there? How is the situation different here? Well, here we have the weight acting downwards on the book. So let's draw it acting downwards like this. Well, as the weight presses down on the table, the table provides a force of support against the weight, otherwise the table would collapse and the book would fall to the ground. And that is called a reaction force, the reaction to the weight of the book. And this goes straight back up. And so you can see the reaction force there is equal to the weight. And so it is stable, stationary, and it is not changing its motion. So what happens then when we have it on the inclined plane like that? What is different? Well, what happens to the reaction force is that if I press straight down on this ruler, it presses straight back. But if I incline the ruler and I press it now, it tries to push my finger back, not in the same direction as my finger is pushing, but at right angles to the surface. So that reaction force actually now comes off in this direction, so right angles to the surface. And one more thing is, if that was the case, you can see that there is a force acting down, which might be counteracted by a force acting up, but there's a force acting to the left here, because this is pulling to the left, that is unopposed, going to make the book slide down the ramp. There is actually another force acting here that acts this time up the slope. So that is called the reaction force, or the normal force, and up the slope we have friction. Now, generally speaking, for this to work, all of these forces need to balance out. So we would need to draw a scale diagram. For this to be stable and not sliding down the slope, then every bit of force to the left must be cancelled out with every bit of force to the right. And so what we would find is we would look at just how far to the left this reaction force is pulling, and just how far to the right this friction force is pulling. Now, if I'd drawn it better, they would be equal to each other. And so therefore there's no sideways overall force. The vertical component of the reaction force, so how much upward force the reaction force is providing, and the vertical force of the frictional force together would have to equal upwards as much force as the weight was equal to downwards. Otherwise the object would start changing motion vertically, lie off or slide down. So you can see that representing an object in 2 dimensions on a free body diagram allows us to work out what it's going to do and how it responds to the forces present in the system. So here's an interesting experiment. I have got a car on this ramp, and what you can see is that the direction that the forces would act, well, there'd be weight acting straight down, there would be that normal reaction force acting at right angles to the slope, and then a force which would be friction but is being provided by this string. You can see that here there would be a force that way, a force that way, and a force that way, and they would have to balance for this not to be moving. But we've rigged this up in a very clever way that if we just unscrew this, you can see that the ramp was not needed at all. In fact, the ramp was there just for show, because rather than the reaction force going this way, this has actually been supported by the tension of this string. But you can see that the angles of those are exactly the same whether or not the ramp is there or not. To hold this stationary requires its weight to be counteracted by one force pulling forwards, a second force pulling back. It all has to cancel out when it's added together. Isaac Newton, when he wrote the Principia, he wrote down all of the basic laws of physics that we use every day. But right at the very beginning, in the first chapter, he talks about 3 things which would later be described as Newton's laws of motion. And all they describe is what forces do. and how much they do it, and how they act. So let's look at each of Newton's laws of motion and try to see if we can make sense of them. So the first law of motion, it tells us about what a force will do. And it begins like this. An object at rest will remain at rest unless an unbalanced force acts upon it. That means that if this is not moving, then it's not going to start to move unless there is an overall force, a resultant force acting on it. So here it is. Fascinating, isn't it? That at the moment all of the forces are balanced on this. Weight acting down, reaction force acting up. Nothing is changing, and so neither is the motion. There are no unbalanced force, so this is staying at 0 meters per second velocity. It's motion unchanging. But this car is also capable of moving, because this car has a little motor in it that will enable it to drive along at constant velocity. This car can drive at any velocity that you like, just change this thing. But when it's driving along, what is the situation then? Are there forces acting? Well, when it's driving along forward, weight is acting down, the reaction force is acting up, there's a driving force being provided by the motor, and there's a friction force acting backwards. And believe it or not, when it's going at constant speed, or it's going at a constant velocity, then all of those forces must still be balanced. It seems counterintuitive. You'd almost imagine that by moving forward there must be a forwards overall force. But no. Newton's first law of motion suggested that it wasn't just for objects at rest, that an object moving at constant velocity would continue to move at that constant velocity unless a resultant force or an unbalanced force acted upon it. This is one of the hardest things to understand, that an object does not need a force to move forward, that it can move at constant speed forward with no resultant forces acting upon it. But to speed it up, to slow it down or change its direction, that is what we need the forces for. Newton's second law is less about what forces are and what they do, but it's more to do with how much they do it. So what Newton suggested was that the more force, the more motion change. And so he then looked at, with his second law, what happens when you have an unbalanced force. So I have here a fan car, and this fan car has got a propeller on it. You see, it's really dangerous. And if I turn it on, it blows air through it, providing a force that is unmatched by any other force. So what's going to happen is its motion is going to change. When I put the fan car on, this is going to accelerate. Let's watch it go. This car has two different fan speeds. It can provide a small amount of force, or it can provide a large amount of force. And how much force determines just how much motion change we see. A greater force will produce a higher acceleration than a lower force. Watch. So first of all, this is the lower force. And this is the higher force. So the more force, the more acceleration. But Newton noticed that something was working against the acceleration, and that was the mass. If I take the same car and I increase its mass, then that same force is not as effective at creating that high acceleration like before. In fact, what happens, the more mass I have, the lower that acceleration for a given force. So there is Newton's first law of motion written down, so that you can see an object at rest remains at rest, I mean not moving, and an object moving with a constant velocity, moving, remains at that velocity, so its motion does not change, does not become anything else, it doesn't speed up or slow down, unless an unbalanced force acts upon it. Newton's second law, looks at just how much a force will change the velocity or motion of an object. And so it's expressed through this relationship simply, that the force is equal to the mass of the object times the acceleration, which is sometimes written as F equals ma. But what does that really mean? Well, it means this, that if the force is high, for a given mass, the acceleration will be high. If the force is low, for a given mass, the acceleration will be low. So force and acceleration are proportional here. More force gives more acceleration. But the thing that's working against it is the mass. If the mass is high, then the only way that these two multiply together can equal the force is if the acceleration is low. And so what happens is the larger the mass you have, the lower the acceleration you're going to produce from a given force. The more massive something is, the less acceleration it's going to be able to go through for a given amount of force. Now there is a required practical on Newton's second law, but we'll do that in a different video. We must now concern ourselves with Newton's third law of motion. Newton's third law concerned itself with how forces actually work. You see, Newton said if object A exerts a force on object B, then object B will exert an equal and opposite force on object A. It means I can't push this without it pushing me. So I put pushing it here, it's pushing back. That these two forces are acting antagonistically. That they're pushing against each other with equal and opposite force. Now, you may at some point have played football. And one of the things that could have happened in football is you could have headed the ball. Now, when that happens, I have exerted a force on that ball because the ball came towards me and bounced off. It changed its motion. So I have definitely exerted a force on that ball because its motion otherwise would carry on over here. But I know, I can feel just how hard that hit me in the head, that has itself exerted an equal and opposite force on me. That you only need to be hit in the face by a football to realise that it hurts. And that is a result of Newton's third law of motion. So Newton's third law is that if object A, that's one of the things, exerts, that means applies, a force on object B, that's the second thing, then B exerts an equal and opposite force on A of the same type. Sometimes you see this simplified to for every action there is an equal and opposite reaction. But don't say that in the exam. Stick to this. If object A exerts a force on object B, then object B will exert an equal and opposite force on object A.